Good morning, everybody. I guess this is, we can start now the first invited talk at the conference. My name is Olaf Schenk, and I'm sharing the first session. And it's a pleasure for me to welcome Doug Kothe, who is the current director of the Exascale Computing Initiative in the US. And he will talk about computational science at Exascale and where we can use this in various applications. So join me and welcome me, Doug Kothe.
Oh, I can. Okay, does everybody hear me? All right, thank you for the invite. I really appreciate coming to the SIAM meeting. In fact, I have a thank you slide at the beginning. I have not been back here. Well, that's a pathetic display. But I went back to my notes, and the last SIAM meeting I went to was 1997, which is pathetic. And we wrote a paper on parallel gather-scatter library back then, John Turner and Robert Farrell. That was a massively parallel era, which for us was about 100 nodes, was pretty way cool. But thank you, it's an honor to be here. And again, this community is really important to the future of HPC, and I think scientific computing in particular, to the SIAM community. And in looking through, believe it or not, I looked through the program and really wished I would have been here earlier. I think I counted 25 sessions where there are investigators who are working in part in the Exascale computing project presenting their work. So just a really fantastic display, and we're really fortunate to have this talent as part of this project. So the roadmap in the Department of Energy looks exciting and daunting, okay? We have some fantastic, we'll call them pre-exascale systems. But there's a recurring theme here that you folks, I'm sure, are very aware of, and that's accelerated node. And I guess I prefer to call it that because these GPUs really are mostly designed for discrete computing, and a lot of times mainly floating point. They're also, as we're seeing moving forward, really designed in particular for certain specialized operations, like those that are well suited for machine learning and AI. And so, the challenge is if we have traditional scientific applications or a mix, how do we exploit that hardware? So I'm going to take you through some examples of at least what I see, and I know I'm going to miss some and maybe get some things incorrectly. So for those folks in the audience that I refer to, you can raise your hand, you can yell out, or grab me later. In any case, our future exascale systems are not so much in the future. In about 18 months, we'll start seeing our first cabinets of Aurora and Frontier come in, and so we don't have a lot of time to really make sure that we're going to be ready. When I say we as a community, but certainly this project as well. The interesting thing about Summit is the box on the bottom, and in talking to Tom Evans, he made sure I got the math correct, but you have theoretically 4.5 billion threads that you could exploit. Now, that's typically not possible. If you think about registers and you think about block sizes, even 32 warps per SM, you're looking at over 2 billion threads right now. And so we're really we're not in the millions, we're in the billions already. So one can only imagine how much, well, it's more than imagine. We really know, I think, it's going to be a lot more challenging and difficult. And there's a lot of really nice, cool things, high bandwidth memory, non-volatile memory. I don't think as a community, at least from what I can tell, we've really figured out how best to use non-volatile memory. Let me also point out a kudos to Jack Dongera sitting back and saying, okay, if I'm not going to exploit the MMA for machine learning, but I want to do it for more traditional things like LU decomposition, I think his mixed precision algorithm that he's worked on with Nick Hyam and Aaron Carson and others, is quite, I never thought I would see somebody use GMRes to do LU, but it worked, and you got 4x the peak performance. And so if you look at the Summit system, HPL in software can be, around 450 on this system, not its peak. The point is, not surprisingly, is software and algorithms is really the way to outstrip hardware roadmaps, and so we really need to focus on that. So what do we do with these powerful GPUs? The other thing too is you look at Summit. Here's a picture of the Summit node at Oak Ridge. You've really got to live on the GPU. I mean, look at the bandwidth. You've got order terabyte per second, okay, and you've got 8 to 10 less than that in main memory. And so you need to get on the GPU. You need to just sit there and live there as much as possible. And we're still, as a community, learning how to do that. We're not, at least in this project, making a bet on any one programming model. You may disagree, but one I think nice outcome of multiple GPUs coming is it's going to force us as a community to have a diverse, robust software stack and not design ourselves into one corner with one programming model. As an app person, that maybe isn't a great piece of news, but that's kind of where we're headed. So if you look at the comparison here, at least for these three systems, and I didn't mention the Sierra system is at Livermore, so a recurring theme here is multiple GPUs per node. So now we got to figure that out. Plus, communicating from GPU to GPU off node, that's something we've got to figure out. A key aspect here is we really need coherent memory, need to exploit coherent memory, and that's here. There's kind of the speeds and feeds. From my own personal perspective, moving from Summit to Frontier, the imbalance in interconnect is better. It's not as imbalanced, I think, as Summit. So the Frontier system, has some common themes: coherent memory, multiple GPUs, a different network, which we're really excited to test and try. In fact, the Perlmutter system at Berkeley will be a great place for us to sleuth out just what Slingshot means in the Dragonfly. There's some nice specs there. So again, we're in the heterogeneous era. This was a slide that Eric Drager made, one of the folks in ECP that I really like. It is the new reality. It's here for the foreseeable future, from what I can tell. If you folks know more than that, certainly let me know. Again, complex memory hierarchy, complex floating point hierarchy, and porting is really kind of a loaded term here, but you're really talking about refactoring, redesigning. And when you do that, you need to rethink algorithms and software data structures, data layout, maybe revisit some old algorithms that were used, say, on the Cray decades ago. So again, in terms of the Exascale computing project, just waiting until these large heterogeneous nodes show up is not the right thing to do. And so fortunately, our Department of Energy sponsors and this community writ large actually started thinking about this. It seems like more than a decade ago, which is good because you need to prepare. And so this project, the Exascale computing project, is I guess in DOE parlance, 7 years is kind of a sprint, okay? And so we want to really get ready in advance. This project started in 2016. And the way, this is a contact sport, so the way you need to get ready is really lots of face-to-face interactions, workshops, hackathons, training. I think every team, if you're an applications team or a software development team, my own opinion, needs to have at least one person who's programming on the metal or who knows it. Abstraction layers are great, but I think you need to also understand the ramifications of choices you make. So again, as we move through preparing as a project in a community for Exascale, it's important to get access to early hardware. And certainly the NVIDIA accelerated node systems, say at Summit and Sierra, are tremendous resources and proxies essentially for what's coming next. So let's do this, okay? The Exascale computing program, ECI writ large, is the DOE program, started in 2016. It's about over a 7-year period, about a $4 billion effort if I include the procurement of these three systems. I'm here to talk about the Exascale computing project, which is applications, the software stack, and integrating those products onto these systems. There's a lot more on our website, et cetera, so I'm going to move kind of quickly. So again, by the numbers, it's a big effort. To show that the whole is greater than the sum of the parts, we really have to make sure that we're integrating together as a project, but also with the broader community, which is why I'm really pleased and honored to be here to share where we are. Not to make the point we figured it all out, but probably to make the point that we've got challenges and issues and certainly could use more help. So there you see, there's a lot of staff involved. 15 of the 17 labs are currently actively engaged, over 50 universities and dozens of industry folks. Let me talk a little bit about applications. That's my background. There are lots of folks here, and I know several sessions that are going to be talking about applications. So each of these teams, or 24 of the teams, has been working at least in this project since late 2016, early 2017, although the applications at our 3 NSA labs have really been working longer than that. These are the applications within our portfolio. What you see here are various pillars in terms of kind of the way we like to group them. the bold, there's a few bold words to give you an idea as to the kinds of things they're focusing on. In particular, we've got a recent publication there that you can look, and it's a kind of a broad overview of this whole portfolio. So what I'm going to do is try to hit 5 or 6 examples here with a focus on the good, okay, and maybe some bad and ugly, but focus on some examples. So Andrew Siegel, I like this slide. He leads our application development effort. And so an application project, we don't just want to see, obviously we want an outcome of these projects is to develop next generation community codes that are really poised to tackle national problems of national interest in the DOE mission space. But each one has a very specific focus on showing their readiness in being able to address a specific challenge problem. And for a lot of our apps, they're on the treadmill, so to speak, for showing they can go 50x relative to circa 2016. And 50x is the improvement in science work rate, so that definition really is specific for an individual application. So what constitutes a challenge problem? I thought I'd show an example. This is Jackie Chin at Sandia. She's leading one of our efforts. And she's a soccer fan. I think her kids play college soccer, so we naturally have the Pele code suite, okay? And this is a very interesting new combustion effort that combines 2 new codes. One's a low Mach number code, Pele AM, one's a compressible code, Pele C, built on a co-design AMR framework that I'll mention later. So you can see that, my main point here, rather than getting into the physics, is these projects are signing up for very specific metrics. They want to show performance on specific problems, okay? And so we've worked hard with the teams to define, what success means in terms of not just rolling on and scaling out on Frontier or Aurora, but doing a real problem and, signing up, frankly, years in advance for what that real problem looks like. Each one of these problems is a problem that we negotiated with a sponsor. In this case, Basic Energy Sciences and DOE, or the Vehicle Technologies Office, as to a problem, which is we really think these RCCI engines are really going to help us in the future. We need to understand them better, and so let's go after that particular problem. So this is an eye chart, and it's more to make the point of leaving behind the challenges. Each one of these applications has what I'll call hurdles, and in many cases, in most cases, they're algorithmic as well as software design. Each application has a very, kind of unique and specific plan. A theme here is multi-scale, and so you see the pluses are combining different scales or combining different physics. Yes, this has been done before, but probably not at this scale, and in many cases, these applications represent fundamentally new capabilities. There's only a few applications that really, where the models aren't changing. I'll say QMC pack is one, and now we're really trying to figure out how to exploit parallelism. The applications in green are those that are on the hook for delivering 50x, and you can see where they are, okay? And these are measured performance numbers on typically Summit or Sierra. Actually, in most cases, I believe Summit, relative to the systems available circa 17. So that would be Titan or Mira. And so you can see some are doing fantastic, okay, well ahead, even actually already achieved. They're not done because they have to show they can do this on the Exascale system for a specific problem. The other apps that don't have numbers by them are on the hook for just basically showing that they can address their challenge problem and effectively utilize the Exascale system, but because they're new, non-traditional, even prototype in 16, they're not on the 50x treadmill, but they are on the treadmill to show that they can scale up, utilize the accelerated nodes, and address their particular challenge problem. So again, this is a leave behind. So we have roughly 3.5 years for these applications to get across the finish line. And for us, for the science and engineering community, that's really the start. These will be great technologies, in my view, to now really go after the deep science in their specific domains. Our job is to get them ready and capable and to demonstrate they can do real problems. And so each one is signed up. And each one of these is led, for the most part, each one of these projects by domain scientists. I'll point that out too, with the teams consisting of applied mathematicians and computer scientists, a lot of you folks, as well as vendor folks as well. Every year we've been reviewing our applications, and Andrew Siegel and Eric Drager in particular, rack and stack what they see with regard to the challenges moving forward. And the focus this past year is again, move on to an accelerated node architecture, really try to understand how to do that, sort of baseline your performance. And right now, there's some, in order of kind of challenges, flat performance profiles, strong scaling, both across the system as well as on node. Really understanding accelerated performance. Right now on the NVIDIA GPUs, we can get a good sense of occupancy, but what does that really mean? We need more performance metrics on node. And recent efforts, say by Berkeley, for roofline models on the accelerators, I think are really helping us understand kind of where we sit there. Choice of programming models, et cetera. Now, let me say something about programming models too, and these are kind of 4 choices. And if you want one in particular, I'm sorry, we don't see that yet. Program on the metal with CUDA, HIP, or SICL, and again, HIP's for AMD, and CUDA and SICL, of course, is Intel. Refactor the code. That's where roll up your sleeves to get down into the trenches, and I think that's not a bad idea, at least for some of your folks, to understand how these architectures work. Offload with OpenMP or ACC. The target offload is coming. It's not there yet, I think, in terms of maturity, but that's certainly what we're seeing in some codes as well. Really past the risk now onto an abstraction layer like Cocos and Raja, and those layers have really taken hold. Of our 24 projects and applications, it's about 50 distinct codes. About a third of those have adopted these abstraction layers, which is really kind of a nice story, because these abstraction layers really were born and raised within the NSA labs, and we're seeing the export of this technology and the take-up of this technology more broadly be real success. I'll also add that in talking at least to Mike Carew, that the end game for these abstraction layers, at least for some piece of them, is to have them appear in the standards, and that the abstraction layers maybe go away or shrink in part and turn over these abstraction layers to the language. And then co-design, which I think, look, there's co-design kind of all the way across ECP. When we say co-design, it's really looking at computational motifs within the application and trying to build motifs that really rock and roll, so to speak, on the accelerated nodes, so the applications can really just live on top of them with these motifs, or at least refer to them a lot in terms of performance. So what we're really seeing, that this strategy is paying dividends. It's been really tough, but we have 6 co-design centers, and thanks to Phil Colella, we have the seven motifs. I think in 86, we now have order 13, I guess, have been identified if you include AI and machine learning. What we've done first out of the gate is really focus on what we'll call the classical motifs for scientific computing. Particles, structured and unstructured mesh, some that are a little bit definitely in the AI space, or machine learning with graph analytics and scalable machine learning, and then also workflows. I'm not going to talk about all of these, but let me give you a few examples. But before I do that, when I say that I think the strategy is working, is we have a number of applications in ECP that are in whole or in part adopting these motifs. Essentially, in some cases adopting them in total and as a framework, in other cases adopting pieces and parts. Maybe for a particle push, I'll use the particle co-design center for that component. So in the end game for the co-design centers is not just best practices and lessons learned. That would be kind of a minimum. It's really trying to develop new next generation components and libraries that applications can actually use. Let me talk about SEED, led by Zanio Kolab. This is a very successful effort already at Livermore, and the focus is on finite element-based PD discretization, unstructured mesh, and in particular high order, which has real attractive aspects on these accelerated node systems, where you get flops essentially for free. You don't have a lot of memory. So now you can, if you go to higher order, you can potentially get as good, if not a better answer on your finite element code with less mesh. And he's really shown, and folks at Livermore, that this is paying off. And they're really putting together a nice package that's out there. MFEM in particular is what they're working within. And you can see that basically there's mesh operations, there's basic finite element operations at various orders, and there's interfaces to solvers and preconditioners, which are really, really important. So this is a kind of a good design, and what you see here is essentially Zanio and his team in MFEM kind of have an abstraction layer, and you can literally choose a programming model for a particular target hardware. There's abstraction layers like Akka, Tim Warburton at Virginia Tech, Raja and OpenMP are available, but also programming more down on the metal through Kothe. And so they're, right now, maybe it looks like a mess, there's multiple options, but I think this makes sense to be able to abstract the hardware away in various ways that you can essentially pick and choose front ends and back ends. And so we really like where this is going. And again, there's going to be a HIP capability for AMD coming soon. And the returns have been very good, okay, for high order, being able to show you're getting order 10x when you're using multiple GPUs as opposed to a single core. And you can see you've got lots of options here. Raja CPU, Akka CPU, going straight to AVX. So they're really experimenting with various combinations, trying to understand what works best for a given application. And so encourage you to look into this technology if you use unstructured mesh applications. A number of ECP applications are looking at it, if not already bought in. So this is a success for us. We've got a community library out there abstracting the accelerated node, giving good performance, and allowing applications that are unstructured mesh maybe focus more on the science and the physics, and at least defer some of this technology to the co-design centers. Another one that's probably more difficult, not that seed isn't difficult, but when a lot of our codes push particles and use particles discretely, whether it's for kinematics, whether it's passive or active, mapping particles to meshes, et cetera. And so this co-design center has a difficult challenge because particles in codes tend to be, sort of infiltrate the entire code, and data structures are everywhere. It's really hard to extract, particle kernels and say, okay, maybe these folks can give me something better. But they made some good inroads there. So this co-design center is known as COPA, Center for Particle Applications, and you can see here on the right, there are lots of great examples in MD. Long range, short range, particle and cell, not just for plasmas, but fluids, and also quantum. So they've had specific targets. And again, another theme here is it's just not particles, because typically with particles in a code, you might have FFTs or other things. So these centers kind of tend to group 2 or 3 like motifs together that's sort of common among an application. And of course, if you're a Barry Manilow fan, if you have COPA, you have to have Cabana. And so here's a library known as Cabana. Stuart Slattery built. It's particle kinematics, basically to understand how can I best push particles on an accelerated node. He arrived at arrays of structures of arrays, began to really program on the metal, realized that COCOS could be a nice abstraction layer. So almost kind of after the fact, he integrated COCOS in to take the place of some of the work he was doing. So Cabana is a particle kinematics library. He's working on a new library to map particles to meshes and meshes to particles. These are fundamental things you need for PIC codes in particular, whether it's plasmas or fluids. Another very successful co-design center led by John Bell is block structured AMR. And again, here it's just not adaptive mesh refinement for structured meshes that are patch-based, but you've got to know how we're going to push particles across these patches. How do I map the patches onto GPUs? Now we break them into tiles to do that. We might want embedded boundaries, so we have cut cells. The linear solvers are unique, typically geometric multigrid. So lots of attributes go into AMR. I believe Ann Almgren's going to be talking about this sometime this week. She's a key person in this project as well. Again, embedded boundaries, geometric multigrid, a very native I/O format. A number of our codes, you see accelerator physics code, WarpX, Astrophysics, a new effort known as MFix, are really all showing progress. In particular, here's some examples where working hard on trying to figure out how to create, destroy, so to speak, patches, map them onto GPUs, push particles, do linear solves, really paid off. You can see some of the performance improvements for WarpX, Order 7X, and a very new, interesting capability that comes out of the National Energy Technology Library, which is laboratory, which is a discrete element method coupled with a CFD approach. Tremendous gains made in moving to AMRX. A little bit about our co-design center for ExaLearn. This is really led by Frank Alexander. It's been going for about a year and a half. It's one of our newer efforts, really trying to understand what can we do in terms of co-design for machine learning? And it's not just scalable machine learning, but it's really more integrating machine learning into our workflows and augmenting and improving and making more productive our scientific workflows. In particular, there are three. I really like the way they've organized the project. Sort of 4 pillars for ExaLearn, and surrogates, control, design, and inverse. Give you a few examples. For surrogates, Peter Nugent's worked with GANs to develop basically GAN-based cosmological images, being able to generate very quickly thousands of images that are very close to the result of, say, a hack simulation over multiple hours or days. And now having thousands of images allows one to do uncertainty quantification or sensitivity studies if you can trust the images. And that's been a really nice effort. So obviously, surrogates is a big win, I think, for things like UQ and sensitivity. On the inverse side, there's been some interesting work there looking at neutron scattering, being able to infer from the scattering spectra what the crystalline structure looks like. So instead of doing a forward simulation, here's a structure, I'll simulate the scattering, generate an image. Now we're going to look at the image and learn. And he's been able to show that he can detect perovskites, which are interesting materials, and be able to do inverse techniques. So that, we're still learning here what we can do and how we can do it, but we need to just get people involved in the trenches and get moving. Let me give you some application examples now. One of my favorites is kind of near and dear to my heart is small modular reactors, and this is a combination of Monte Carlo neutronics and CFD, and it's coupled. So you have complex flow moving through a reactor coupled to neutronics, which sets the heat source. And you can see kind of where some of the goals are for neutronics and CFD, and basically it's higher fidelity, better resolution of the geometry, and et cetera. In particular, this project has 3 codes: NEC-RS, which is essentially a GPU or accelerated node rewrite or refactor of NEC 5000 with Paul Fisher. This application is heavily relying on SEED, the Co-Design Center, and then 2 Monte Carlo applications, Shift and OpenMC, that are each taking different approaches. And that's important to take, I think, some parallel redundant approaches in terms of how to exploit performance. Interestingly enough, Monte Carlo you think would parallelize embarrassingly parallel, and it is, but it's not so good for GPU if you're history-based statistics. Meaning, if you have many particles on a GPU, in a case of neutrons, you wait till all of them go from birth to death, or essentially are absorbed or scattered out of the domain. And you can see that a good example here is you might have thousands of particles, and most of them are done after a few collisions, but you have this long tail, and the GPU sits there idle, waiting till all particles are processed. So a history-based statistics is really not the way to go. Instead, it's better to do event-based statistics and group them in groups. Who's going to fission, who's going to scatter, put them in groups. It's speculative, admittedly, and then process via warps, all like particles. That didn't quite get you there. You need to also say, here's a region that's very specific. It's the fluid, or it's the fuel, or it's the steel. So you also then bend them by regions, and basically what you can get. And this group is about a 50,000 line piece of code. They had to essentially unroll the loops and sort of wholesale redesign that took order a year to do. So it wasn't necessarily easy or overnight, but got good returns, order 10x faster on node. And projections are 20x factor relative to the CPU algorithm. And so that work's published in an example of going to a new algorithm. And actually this event-based approach, Forrest Brown of Los Alamos was doing this in the 80s on vector machines. So Back to the Future. Molecular dynamics, this is a very interesting problem that I really like, EXALT, and led by Danny Perez. Steve Plinton, who's here, is part of this project as well with his LAMPS code. But now you're talking about orchestrating thousands of LAMP simulations to do replica dynamics. And on the fly, you may be talking to a code called Latte that's doing DFTB calculations on the fly, quantum forces, doing potentially some machine learn potentials on the fly with Snap. Anyway, it's a great story in that you put an eclectic team together, in this case, looking at a specific kernel, in other words, a snap potential. And I say that meaning our vendor partners like NVIDIA and Cray and performance engineers at Berkeley, and really good things happen. In this case, taking a hard look at the snap potential, which is a heavy sort of compute-intensive potential. unrolling the loops, reversing the loops, peeling apart things, led to order 200x improvement, which is certainly you don't plan a fantastic outcome, but it really shows what happens when you put different folks together that maybe haven't thought about things the same way, or even come in kind of fresh. So this is a great example of a nice result. ExaWind, predictive wind farm simulation. So now you're talking about modeling not just one wind turbine and resolving it with an unstructured mesh as the turbine moves, but you've got a background fixed mesh. But now you want to go after a turbine wind farm, order 50 turbines instead of one. Okay, the one turbine problem is difficult enough. It's for the most part, I would say, solved, although the turbulence models are open. But this group, led by Mike Strave at Inwell, wants to go after multiple turbines. And the Exascale problem is ideally sort of a whole wind farm. And as noted in the previous slide, when you put a bunch of these together, the potential energy of converting wind to electricity, you lose about 20% because of the turbine-to-turbine interactions and the buffeting. And you understand what those interactions are like, and ideally be able to automate and control the turbine motion real time. Two interesting codes here: a new incompressible code, Nalu Win. So you've got an elliptic solve. You've got to make those solves scream. There's a strong scaling challenge. And Open Fast, which is the background code. So you map the rotational forces of each turbine onto the background code. So this is a good example of moving the GPUs. Well, they focused early on KNL. That's not a path forward. But then when they worked on KNL, they used the COCO's abstraction layer, so that work was not wasted at all. Okay, complications with regard to mapping meshes and moving meshes, and the abstraction layer in particular needed to move forward. Okay, so what was the challenge? Well, not surprisingly, strong scaling performance of the linear solves. And so the Hyper team at Livermore really got involved, some nice innovative work in trying to figure out how to I'd view it as cheat and reduce the global reductions, and got a nice result with regard to low synchronization Gram-Schmidt. So this is an example where challenges and issues arose in the application, and it flowed down to the applied mathematicians like this community, and they really worked to develop better solvers. And so there's still challenges ahead for this application because of the strong scaling. Stellar explosions, very interesting, and I've had folks say, well, you guys don't have a lot of multiphysics apps. This is as complicated as a multiphysics application as I've ever been around experience with. Anshu Dubey is here, and she certainly knows, and is a part of this project. The thing I like to point out is you've got lots of different physics here: hydrodynamics, gravity, kinematics, nucleosynthesis, radiation transport. In this case, is neutrinos, not neutrons. Neutrinos are nonlinear, neutrons aren't. You got an extremely challenging problem here. What's interesting, and I talked to these folks early on, I said, you guys really need to come together and bring your codes into one framework. So not surprisingly, they called it Clash. Okay, lots of different codes, and basically living on top of, in part, the AMRX framework. The thing I like about this project too is, let's do, maybe we're not going to go all in on a particular programming model. So let's look at OpenACC, let's look at OpenMP, do some comparisons there. You see with the radiation transport. Let's move the hydrodynamics to GPUs. Okay, we're going to get good performance there. But when you couple, now you got to think about who's the CPU hog, who's the compute intensive, who should go on the GPUs, who shouldn't. So when you bring in multiphysics, that's a more complicated problem. In this case, not surprisingly, getting good performance by putting the radiation on the GPUs. So the point is, with multiphysics, things get even more complicated. Another project is additive manufacturing. This is just as led by John Turner. Really complicated, lots of different codes, trying to understand how do we go from melting and solidifying, where the laser hits the powder bed, on up to residual stress and strain. 3D printing of high-spec metal alloys is really still an unsolved problem, in that you do get high rejection rates. So this particular application is looking at trying to understand fundamentally what's going on in 3D printing, in particular with certain high-spec metal alloys, so we can improve the process. A little shameless plug here. I was involved in some particle pushing back in the 80s, and it's kind of neat to see this project pick up some old methods for particle itself for fluids and solids. And in particular, the particles in this case really used more traditionally for plasma physics, but I don't think a lot of people know that they really were born and raised kind of in fluids and solids. So this project is looking at some old methods known as FLIP and MPM, and this one I really like because Joy Turan at UCLA picked up this method and used it for computer graphics. In fact, if you watch Moana or Frozen, most of his technologies, which is real 3D, Navier-Stokes, and material stress and strain, used in those movies for animation. He's been brought into the project, and there you see the particles. This is an MPM approach to really say, okay, can we build a new particle code for additive manufacturing by looking at that melted chocolate rabbit? You might go, okay, maybe that's sort of what we want. And so there's a new effort here that I think has promise. I think Stuart Slattery is here in particular, which is to build a new particle-based code to go after additive manufacturing. Like I noted before, particles, they're embarrassingly parallel, but it's not easy necessarily to put them on accelerated nodes. The final application I believe I want to hit is IMFIX EXA. This comes out of NETL. And here, doing a chemical looping reactor, you're talking about fluidized bed reactors where you have particles and you have a gas flow up through the bed. And so the gas flow is sort of traditional gas CFD, but now you're gonna model the bed with billions of DEM particles. So their goal, you can see, has very specific goals. So it's sort of 5 billion to be able to do a pilot reactor. These CLRs, if you look them up, basically are an interesting way to burn fossil fuels, say pulverized coal as an example, and really just emit CO2 rather than NOx and sulfur. And so, not surprisingly, IMFIX says, well, we have pushed a lot of particles, let's just live on top of AMRX, literally just as the entire framework, which is a really good story in my mind. So again, past the parallelism and the accelerated node performance on to a co-design center, in this particular case, John Bell's AMRX. So that is one way of going about it in terms of application development. There's a lot of other. Look, I want to convey that we've made a lot of great progress, but I also want to note that this is hard, okay? This is really not easy, but I do want to point out some other efforts in our chemistry applications. We're doing analytics for light sources, power grid, graph analytics, and nuclear physics are just a few examples. And while I was kind of focusing more on the speed up, it's really about the science, okay? And the science drivers are driving our development. But in particular, we've seen some nice developments with regard to these applications. So I won't have time to dive into those, but I do want to point out that all of these projects are, I think in the last year, we've kind of seen them turn the corner and making some real progress. I really like what Andrew Siegel said last week at our annual meeting. There are a lot of lessons learned, and if you listen to Andrew talk, you kind of walk away going, wow, this is really tough, and it is. So these are his top 10. And let me just point out a few. I mentioned the billions of threads. Okay, that's pretty daunting. Fast processors are just going to sit there. They're going to die if you don't keep feeding the beast. Okay, you have to find more work while memory is decreasing. High order is a good way to go. That's what the SEED project chose to do. Weak scaling problems are still important. But these GPUs perform very poorly when they're near their starvation limit. Again, I won't go through all of these, but actually the accelerator architecture is limited by Amdahl's law. That's a good point, because there's a lot of latency involved with copying from the device to GPU. You need to really try to live down on the GPUs or the accelerators as much as you can. There's definitely some penalties to pay there. Now I want to talk a little bit about software technologies in just a few minutes that I have. Mike Carew leads this area, and Lois Kerf-McGinnis is here, and she's his deputy. And basically, a lot of the work that I mentioned on the application side really leans heavily on the first three in particular: programming models, runtimes, dev tools, math libraries. Certainly, data and viz are very important for what I would call real scientific workflows. Not that our challenge problems aren't real, but the workflows themselves are really critical for delivering the answer. So there's been a lot of effort in ECP in and not just sort of fundamental algorithm development, software redesign, but integrating into applications, integrating into our facilities, and packaging things up in a way that really reduces the barrier of adoption. Okay, and I want to talk in particular about that. So as we know, in this community has worked very hard to open source their products and deliver good products, in sort of ones and twos. Okay, this has been the traditional development path. But we realized, Mike and Lois in particular, first for the math libraries, that by packaging similar functionality together in software development kits, there was a lot of advantages, not just for the consumer, the application, but for the like applications themselves, being able to interoperate, being able to have consistency in build, being able to leverage one another to potentially reduce redundancy where it made sense. And so SDKs, our math SDK is very mature, and I got a slide that shows that. But the idea is, okay, how can we take this broader across the entire ECP portfolio, in particular develop a stack that is not just here to allow us to complete the project successfully, but it's here for the duration. And so let's think long and hard about deployment, continuous integration, CI/CD, and testing in particular. So, I like the slide that Mike showed last week, which is our legacy, is just not sort of declaring success in ECP from a project point of view, but really having an open, hierarchical, and extensible HPC software ecosystem, and what we hope would be a model for post-ECP, which would be beyond 2023, continuing this effort. And I feel confident, although it's not my decision, but I feel confident our DOE sponsors will work with us to continue what's been started here. So I encourage you to go to e4s.io. Even I've been there. There's some nice, really nice instructions for people like me about grabbing the current capabilities that are there. The latest release, I think, was just last week. Is that right? I'm looking at Lois. Was that right? Just last week. 50 full release and 10 partial leak products. Samir Shindi has been fantastic. I think I spelled his name right. In really being on point for this development. So you'll see, build from source binaries. You'll see 4 different containers. There are lots of different ways the products are out there. So please go, give them a test drive and let us know what you think. In particular, this gives, I think, a really good example for where various software technology products are with regard to looking at accelerated nodes. And so working with, say, with CUDA on the NVIDIA GPU is certainly a great proxy, so to speak, for what's coming, meaning we think the hard work is about rethinking structures and rethinking, execution, and the semantics of the different languages we think is not as important as the conceptualizing. So again, this is just to note that there is progress. I think this time next year we'll have a lot more to say when we get a lot more hands-on with regard to the Intel and AMD hardware. We're just beginning to get there. So again, the idea, performance portability is often a journey, not a destination. We recognize that. That's really hard. But really to be able to have a software stack that's very robust and able to abstract or help you with regard to these different accelerated environments. So again, we look at the math lib, or the XSDK, as Lois calls it, but the goal here in ECP is to componentize and package our entire product portfolio, which right now is about 70 pieces and parts. So I encourage you to go to the website. You can talk to Samir or Mike or Lois about what we're doing here, and potentially influence us before we're not going to call it good in 2023, but we have very specific metrics to get there. Also want to point out the scientific productivity and better scientific software effort, also led by Lois and Mike. There's a nice new report out about kind of best practices, lessons learned with regard to, and I would say in particular as an application first, and the application community can learn a lot about how to develop better software, how to be more efficient and productive. Relative to a decade or so ago, there are common tools and technologies. SPAC in particular is fantastic as a package manager. Jenkins for testing. So we're seeing more and more applications and software teams using the same things, which really helps ECP. Also want to point out, if you want to get a sense of the ST software technology portfolio, Mike Carew and his team work hard to release kind of a new version of their report every 6 months or so. There's a new version that's just, I think, a week or so old out on our website. It gives you I'd say a 6 to 8 page summary of each of the products in terms of what they're doing, where they're headed, really a nice assessment report. And I'll just sort of echo the comments of Fred Johnson, former DOE program manager, which is, where was this 20 years ago? In other words, this is a great sort of nice summary of what's going on here. And again, not claiming that everything's right or perfect or we got it all figured out, but at least you as a community can see what we're doing and engage with us. So recent advances in software technology, okay, and I promise I'm almost done here. I focus a little bit more on applications here, but there's been a lot of fundamental effort. I mentioned a little bit about the solvers. We're really betting big on LLVM, Barbara Chapman and Jeff Vetter, and there's been a lot of progress made there with regard to OpenMP, intermediate representation. So I can't emphasize enough how important that open source compiler environment is for us as a community, certainly ECP. Some nice developments in math libraries, sundials, ODE solver, really used heavily in particular by combustion. Jack's effort in Clover. This is just one example. So what I did is I picked some things out in terms of kind of what we've seen the last 3 or 4 months. This is very recent developments. FFTs are a motif in and of themselves, and so just want to point out that Jack's working hard on highly efficient FFTs, as is Phil Colella. So that's a key technology. Performance monitoring with software-designed events. I mentioned SPAC. That's just been a tremendous success. Todd Gamble and Livermore, it's been a huge uptake. We didn't require it in ECP, but most of our PIs are using that package manager, which really helps us understand across our portfolio, have metadata that's really the ground truth of who's using what, when, and where. And I/O is very important. There's been lots of nice developments in terms of asynchronous I/O. Mike also has his lessons learned. He is a real process guy, and I mean that with all the love, okay? And a lot of his lessons learned are about, software development's an ugly process. It's very agile, but you can kind of put some boundaries on it and measure progress and be able to commit to some things. I think as a community, he's done well in really driving that. But again, there's his thoughts about preparing for exascale platforms. Can ECP help you? I would hope so. And so as you move to accelerated nodes, look at what we're doing. I guess I would sort of modify the weight. I would say, maybe now's the time to take a look if you haven't tried this. Again, we have massive concurrency, we have massive latency. I mentioned that. That's kind of what Andrew Siegel pointed out as an Amdahl's law issue, right on the node. Okay, what you do in the GPUs will generally map back. I mean, we've seen that for decades. Focus on one architecture, it generally pays off in others if you're careful. Parting thoughts. Again, it's here to stay, heterogeneity. This community is really important for scientific computing and the convergence with AI moving forward. So I think the SIAM community in general doesn't have a problem in integrating out with the community. So this was admittedly, I was thinking about one particular, domain scientists in particular tend to kind of live in echo chambers at times. And so what we've seen in ECP is this forced integration and culture clashes that I think have really, really paid off, where, domain scientists, and we have some of the best in the world, I kind of see some one-upmanship, and I think that's good. One project looks at the other and goes, boy, I think I can do better than that, or how did you do that? So this sort of interaction is really important. We do lots of training, lots of hackathons. That's really a fantastic way to go about it, engage in that. I can't emphasize that enough. We've got lots of lessons learned, maybe not so much best practices. Hopefully you'll see that in some of our documentations. Again, if you want to go fast, go alone. If you want to go far, go together. Or I guess I didn't realize I mentioned it before, but this is contact sport, so I'll credit that to myself. This is not easy. So if you want to look more carefully at what we've been doing, in addition to our website, there's an ECP annual meeting we held just last week, and there'll be lots of posters and presentations being uploaded very, very soon. So that's another place to go. So reach out to us. In particular, I'm a talking head here that doesn't do so well at it, but this is the senior leadership team we're blessed to have some fantastic leaders in the community. I didn't mention Lori Dyson, who's been just fantastic as our deputy. Andrew Siegel and Eric Drager lead the application effort. Mike Carew and Lois, software technology. And I really didn't mention the hardware and integration effort by Terry and Susan. And that's really been important in deploying our software products and our applications and engaging performance engineers with our applications to make sure that things are working well. And what I call our facilities are really the big HPC centers in the DOE labs. And so I apologize, just didn't have enough time to get into that effort. Maybe there'll be a next time. But in any case, I've worn out my welcome, I think. So thank you for your time and attention. Appreciate it.
Okay, thank you very much, Doug, for the talk. So is there any question? Maybe in the interest of time, because we are 5 minutes late, is there questions somebody would like to ask? Yes, there's one. Could you please use the microphone?
I can hear you and repeat. Yeah, so look, I mean, me standing up here giving a 45-minute talk doesn't really, scratch that itch. We have an industry council, okay? And yes, and good, but the industry council is not a scalable process. So we're really interested in getting. So let me also say that from my perspective, again, this is Doug speaking, not DOE, but we've not done well in translating our research out to industry. And so we are planning things like deep dives where we'll spend a few days with a group of you folks. We have one actually planned in early March. And a deep dive is, you heard some things that maybe are of interest. Let's bring the PIs in and talk details, okay? Exxon is probably an application development. You do application development as well as application usage, correct? So my guess is for that class of industrial partners, you're likely to not swallow one of our applications whole. You're probably likely to look at pieces and parts or the software stack in particular. So in that case, I mean, I do feel strongly that the E4S and the SDKs are really technologies that you should look at seriously and look at, biting the bullet, so to speak, and bringing them into your software stack. That said, we have open hackathons and training sessions, and I think there's where too, we just need to make sure that we're having them and that you're invited. And these are fantastic because we have folks from NVIDIA or AMD or Intel who are really close to the metal that come in, and you bring in your code kernels if you can, and just work through that week to try to figure out what to do and how to do it. But on that note, our sponsor in a review in December noted that our outreach needs to be better and put us on the hook for more aggressive outreach. And it's a combination of, meetings that are one-on-one, certainly presentations, but getting lots of documentation out. But I recognize that problem. I think we can do a lot better, and our sponsor does too. And so we're really on the hook to do more aggressive outreach. So please just contact us if you, have thoughts about how we can do that better, because I think it is an area we need to improve.
Okay, great. So thank you very much for presenting the entire ECP initiative, and please join me again, and thanks, Doug, for the presentation.